Welcome, everyone, to the next in our series of virtual consulting offices. My name is Diana Sinton, and I'm a project manager for iGuide. Today, we are going to hear from Dr. Debayan Mandal about his work with digital twins and urban flood dynamics. iGuide is happy to be able to offer these sessions almost every week. We use regular Zoom meetings for them, so please, you're responsible for controlling your own microphones. We have an opportunity for questions and answers at the end of the session, and you're welcome at that point to be able to turn on your mic if you like, but please also feel free to put questions into the chat, and we will address those at the end of the session. We have a screen up there that's showing you that we have what the next two upcoming VCO topics are. We're about to begin several weeks of having our 25-26 cohort of UCGIS community champions sharing their work on the materials they've developed to support our convergence curriculum for GeoAI and data science that uses the iGuide platform to both deliver and support those materials. So that's a pretty exciting collection that's going to be highlighted soon. Let's see, we are a couple minutes past the top of the hour, so I'm going to stop sharing my screen and turn it over to our speaker. And thanks, everyone. Thank you, Debayan, for being part of our group today. And I'll turn off my mic and camera and see you later in the question and answer time.
Sounds good. Thank you for hosting me. Hi, everyone. Good morning. Thank you for being here today. So I'm Debayan Mandal, and I'm an assistant teaching professor here at ASU at the School of Geographic Sciences and Urban Planning. And today I'd be presenting my work titled Strengthening Resilience in 4D Geospatial Digital Twins for Navigating Urban Flood Dynamics. So before we begin, I'd just go into a little bit of the topic. So we are sort of observing an increasing frequency and severity of natural disasters worldwide over the past few decades. And alongside this, we see that there has been very uneven distribution of disaster impacts across various communities if we see it at a very micro granular scale. So to combat this, first and foremost, we need to build resilient communities. And to do that, we need tools, frameworks, which would help these communities understand or prepare for or respond to these events, right, at very fine resolutions. So if we consider, for example, in these four levels, right, if we consider a very high caliber flood event, at a very regional level, you'd see that there is widespread inundation, disrupted connectivity, and even overwhelmed healthcare systems at the city level with critical infrastructure damages, water supplies contamination. We have resource shortages. At building levels, you can get building damages, undermined foundations, electric plumbing failure, mold and mildew. And at individual level, you can have long-term health and financial consequences. So understanding this multi-scale sort of recognizes the cascading effects of disasters and that our world is very interconnected, and we need to take into consideration this regional differences that we have in the face of hazardous events. Now, specifically, the work I'm doing is based on urban flood, even for our digital twin. So let's look at specifically urban flood challenge, right? So how critical is this problem? At the study area that we are doing, we see that if we even take First Street Foundation data, right? A flood with 1% annual chance of occurrence, which is like a 100-year flood, it is projected to affect about 27,000 or above properties in that study area. Now, in a time where the majority of the homeowners opting for 30-year mortgage, there is about 26% chance of that flood event occurring within the mortgage itself. So climate change projections, if we see, that indicates that even more properties will come within these affected zones. And so at micro scale, if we look at this, there are various challenges. At first, we see that there is a lack of 3D perspective that we have. So we don't have a 3D perspective in resilience management or planning. If we get a 3D perspective, that even improves the risk perception amongst the stakeholders that we have, because the inherent 3D quality improves how they perceive disasters happening, what flood depths are, how much flood velocity would take place near their buildings, so on and so forth. Second, we see that most of these models that we use today, these are static. They do not update in real time, right? And so they limit their use in temporal aspects of this flood management. And in third, we see that there is very limited stakeholder management. It's more of a top-down transfer of flood maps. We don't see the public engaging with technical outputs because they are not often not very intuitive. And fourth, we see that most of these models cannot assimilate live data for forecasting. So there is a lack of real-time adaptive capability. And finally, conventional 2D maps that we have, they fail to give you the temporal dynamics of what's happening. But fortunately, we have this opportunity by synergistic multi-scale disaster resilience. If we take into consideration the theoretical and technological advancements that we have gotten, for example, CyberGIS is providing us with high-performance computing infrastructure, which can expedite processing speeds with significantly greater resources. And we can overcome our latency, computational bottlenecks through our parallel computing. Now, the digital twins, they have the unique ability to simulate the hyperlocal effects of these hazards. It can be varying types of hazards, but here we will focus on only flood and different kinds of built environment scenarios. All of them can be informed by real-time data. So they do bridge the gap we have between simulation and then the reality. And finally, the social sensing platforms. They would provide individual level real-time sensor information. Every person becomes a sensor, every stakeholder becomes a sensor. And we can get a lot better idea by harvesting data from, say, citizen reports. We can get harvesting data from social media, other crowdsourced channels, so on and so forth. But so let's look at the phases of the disaster so that we can understand how these capabilities sort of factor in there. Okay. So, disaster resilience, we see that they're often conceptualized in four main distinct or interrelated phases in most of our literature that we have: mitigation, preparedness, response, and recovery. And each of these phases would need synergistic interventions, both in the macro scale and the micro scale. Now, at macro level, obviously, we have a lot of frameworks and dashboards where we focus on informed policymaking, say during this mitigation, customized risk assessments for preparedness. We can have targeted relief operations to the vulnerable communities that we have during the response period, and rebuilding resource allocations to the least resilient sectors when we go into recovery. But then we see that these requirements are facilitated by CyberGIS through integration of large-scale spatial hazard and demographic socioeconomic data. We can have risk assessment methodologies, but at a micro level, emphasis then turns into localized knowledge, risk management, and only specific community needs. So the mitigation would call for protection features, for example, permeable pavements, levees, low impact developments, greens infrastructure. Preparedness would focus on developing localized risk perception, where the 3D model really helps amongst the stakeholder. During responses, we need real-time data from either social sensing or live monitoring systems. And recovery would be driven by localized rehabilitation. We can have commercial reopening, efforts to stabilize the local economy. And to this end, we see that the digital twins are invaluable because they support all these at a very hyper localized simulation of for our example, we are focusing on urban flood, but most other disasters as well. So to give it a context, digital twins were defined by Nazim as a set of virtual information constructs which would mimic the structure, context, behavior of the natural, engineered, or social system, and dynamically updated with data from its physical twin, have a predictive capability, informed decision that realize value. So to get from there, we have basically four salient features. First, a digital twin needs to mimic the context of the physical counterpart. Whether it's environmental or it's a social system, it needs to do that. Secondly, it needs to incorporate real-time data analysis so that it's dynamically updated with the data which we have from the physical twin. Thirdly, it needs to enable modeling of what-if prediction scenarios. It needs to have predictive capacity. And fourth, it needs to inform decisions that realize tangible value for the stakeholders. And these features collectively make geospatial digital twins a very powerful paradigm for urban flood resilience. Now, let me walk through the evaluation or evolution of digital twins. We categorize them basically in three formats. One is a digital twin instance, digital twin aggregate, and digital twin environment. We see that digital twin instance is basically a single snapshot representation, one event, one instance. Then digital twin aggregate, a DTA, that integrates multiple of these digital twin instances, and then gives a predictive capacity with design storms, real-time radar input, digital twin environment, which should combine diverse domain aggregates and integrate socioeconomic, environmental, infrastructure systems into one unified system. Now, globally, we see there's a few examples with virtual Singapore, Herrenberg in Germany, Helsinki 3D Plus. And in our project in FlowsDT, this is a digital twin aggregate that we are working with real-time flood forecasting ability. Maybe at a later point of time, we would advance into digital twin environments. Okay, let me now outline our specific research objectives that we covered. First, we aim to develop a comprehensive geospatial digital twin, which would integrate detailed topography, hydrography, built environment with very high resolution. Secondly, we cross-validate this twin using 4 historical flood events and ground truth that data, and we derive that ground truth data from various areas. We extracted flood location information from news articles, web pages, social media, all of that. Thirdly, we modeled hyperlocal urban flood conditions under 5 design rainfall scenarios: 2-year, 10-year, 25, 50, and 100-year return periods. And finally, we quantified these flood impacts, the depth, extent, velocity, duration on, say, buildings, roads, critical infrastructure under these various different scenarios. And Galveston here was an ideal test bed for us because it's the coastal barrier island in Texas, and it suffered multiple forms of flooding over the years. So let's look into the methodology here. First, we took the land use land cover data, imperviousness percentage from there. LiDAR data gave us the topography, and with an watershed delineation, we got the subcatchments. The subcatchment properties were obtained from the LULC. And from the subcatchments, with the watershed delineation, we also got the natural channels. Storm sewer geometries were obtained from the city website, the city GIS assets, and corrected to form the inlets, outlets, and conduits. Together with the natural channels, these will make us a 1D modeling system or a 1D conduit model. So we used for this Manning's equation for routing, dynamic wave method, Horton infiltration method. We are going to come to that a little bit later more. Now, for the 2D one, from the LiDAR data, we got the building meshes, and from the building, keeping that as obstructions, we obtained 2D hexagonal meshes. And these 2D hexagonal meshes we took as about 780 square meter cells. But there was adaptive meshing around the buildings depending on the building sizes. And finally, these two were coupled using orifices. So there was bidirectional surface to sewer flow. It took into consideration surcharge when it exceeded capacity, also the energy loss equations, and all of that. Okay, and all of these went into our PC-SWIM 1D, 2D coupled modeling. We got our data set for validation from the news articles, social media. We picked out four different heavy rainfall events where we could figure out places of high flooding. And then we had the rainfall gauges, two rainfall gauges from where we entered our rainfall, and then got our flood volume, flooded nodes, flood depth, and flow velocity at building levels, road levels. Now, there is a manifold usage of this digital twin, some of which we will demonstrate. One is the design rainfall scenarios through the SCS symmetric method. Once we use this, we can incorporate that through the rainfall gauges into the modeling and get flood risk at different places, given new buildings or structures. Structural interventions like low impact developments or pipe sizing, we can see or find out its effectiveness without constructing it, but previously as a modeling scenario. And finally, we can add in the NWS radar data into our rainfall analysis program with a real-time update so that the model can give us real-time flood forecasting. Okay, so this was our study area, Galveston City. Like I told you before, this is a coastal inland city with an area of 209.3 square miles. And we saw that the properties at risk in a 100-year flood was 26,651 out of 28,244 buildings. And this is a representation of the elevation, and then this is for the imperviousness. So in the urban context that we have, apart from, say, natural hydrology, we see that subsurface drainage network that plays more of a significant role than our natural channels, so as to how runoff is conveyed. So we needed significant data curation to get our storm sewer geometries to formulate a well-connected system that we needed. And the raw 2D data that we had was converted into 3D system with a lot of corrections. So let me highlight a few curation steps. We used, network segments. So orphan network segments that we have, like which had no terminus at water bodies, that those were excised. Some of the missing inlets were supplemented at adjoining pipe diameters with very low slope levels. If we had superfluous bends, unnatural bends at the pipes, we streamlined those. The inlets with missing depth, those were given the same diameter at the adjoint conduit. We used the strategic conduit additions so that there was hydraulic connectivity. We had several network systems that were not connected together. We used new conduits in between them because offhand stream networks between the cities made no sense, right? And then parallel pipes that we had, as you can see over in this image, from the Bay Park to the ocean, we consolidated those into barrel structures with very analogous dimensions. And then the natural flow path that were connected to the storm sewer junctions, those are based on spatial proximity. And so this was our coupled modeling network, as you can see, from the impervious area to the junction conduits to the downstream subcatchment and going into infiltration losses to the subsurface layer and the junction and conduits. From there, the seepage through pores, all of these go into infiltration to the aquifer recharge. And we use this top example here because the impervious area for us was the street. And then those storm sewers was the junctions and conduits, with the sewer manhole, the sewer pipe, and the street inlet. And our final network, after all those corrections, was comprised of about 1,638 conduits, 1,529 junctions, 4 dividers, 100 outfalls at just the 1D system. These were our equations used. So for the surface runoff, we used Manning's formula. Infiltration analysis, we used the Horton model. And for the governing equations, we used the St. Venant's equation, so merging the continuity equation and the conservation of momentum. So together, PCSwim software that we used, we performed the 1D flow computation in the conduits and pipes and the 2D flow computation for the overland using sheet flow, and then connected it together. Okay, so this is just output of that. We identified and modeled about 4 events, 14th May in 2010, 4th June in 2016, 18th April in 2017, and 29th September in 2018, because there was really extensive data that was found in these. And the flooding was mostly due to heavy rainfall. Otherwise, if it was compounded with, say, storm surge, we'd have to connect storm surge dynamic models into the coastline over here with different storage tanks. Okay, so here we are showcasing the results for flood depth and velocity in 4th June 2016. As you can see, we have the 2D format first, but then also a 3D format where you can zoom in, get to your neighborhood, and see how the water changes based on, say, a modeled flood event or even a design rainfall scenario. Okay, so this 3D visualization that we see that uh, this helps a lot in the risk perception because people can move in here and get into their own location, places that they are more interested in. So for the stakeholders, for the city people, providing this multidimensional perspective for potential flood scenarios or flood events sort of enables more comprehensive understanding of their impacts, right? So let me also go into the underground format. This also gives us, yeah, this. So we also see the underground sewer system whenever it gets surcharged based on the capacity and then floods into the overland area. So on the top inset, you can see wherever there is more flooding than the manhole capacity and the sewer system capacity, it floods into the overland, goes into the meshes, and we see how much flooding is happening. So this sort of gives us both overland and underground view with a level of detail of 4. So there is a much robust communication of risk between the city authorities and the stakeholders of the community. So I'm gonna just move this forward to showcase this event. So I I hope we notice that this is a lot more intuitively understandable. So it requires all of the parties that are involved, the stakeholders, they can visualize and grasp what the potential outcomes would be without giving them technical maps. And this, for our temporal spread, I just want to showcase this small wet patch over here to show how accurate this modeling could be. That when we created the flood extents, we can see over these areas, this exactly forms the wet patch area whenever this flooding had happened. And this is, I believe, the September flooding. Okay, so there is immersive 4D visualization. For the above ground, we see that the 3D flood depth is there. We can get the extent relative to the building heights. We can also get velocity textures. The velocity for Galveston here is very less, which is why the velocity tracers are like small dots. But when there is higher velocity in the flooding, you can see how the flood is or water is moving as well. And below ground, here we can see underground view of the storm sewer system. In the video, we showed how it, over time, you can see how much surcharge is happening. And this also comes with interactive pop-up displays, like when we select on different conduits, you can see how the flow and depth changes over time. So this gives us this 4D advantage: length, breadth, height, and time. Stakeholders can visualize how much flood rise is happening, how much recession is happening. We can find out test scenarios. So there is a cross-agency collaboration that can be done here. Okay, subsequently, I want to present some stage hydrographs at various of the city locales so that we can showcase, sort of demonstrate the diversity of flood behavior that we have. So first one here, and I'm gonna zoom in a little bit so that we can see better. So here we see that this area is really well connected, right? With the natural flow systems, as well as there is multiple inlets, as you can see over here. So on the top, we have the rainfall. We see the flood depths. It does not really last very long. It quickly recedes. On the other hand, if we go into this area, we see there is no storm sewer infrastructure. And so we have a rapid influx of flood water from adjacent areas. But then there is a gradual decline in the water levels because there is natural flow paths. And finally, I want to showcase this area, which is a largely marshy area with low elevation. And you see that there is no natural channels going out of there. So there is ponding or accumulation of water. So there is no drainage. And there, even after a long period after the precipitation has receded, we see the water is still standing there. Okay, so for validation, we did not really have stream gauge data for our flow. So we had to focus on identifying high water regions to validate our results. And to do this, we had three avenues: news articles, web pages, and social media. And for this purpose, we used FFIR, FFBIRD, and FFNER to extract locational information of these model events. And I'll just give you a brief overview of what these does. FFIR would retrieve documents like social media posts, news reports, government records, and so on and so forth, other kinds of documents from web for past flood event, whichever flood event of interest or date we can give it. Then FFBIRD that classifies the paragraphs contained in these web pages that we retrieved into different pertinent categories like damage, fatality, and other scenarios. If any are, these extract specific information, for example, impacted neighborhoods, streets, and classify these as different damage categories. So we finally obtained something like this. On May 14, 2010, you can see Pleasure Pier and Stewart Road was affected. June 4, 2016, we could find information of lower portion of Greens Bayou being affected, Broadway, Harborside Drive. April 18, 2017 had a lot of more information: Galveston Island, West End, Galveston Causeway, the pier, the Pelican Island, and so on and so forth. There are several of these that we find that get repeatedly affected when we did design rainfall scenarios, but we'll come to that in a bit. September 29, 2018, we see that downtown Galveston, Galveston Strand, Broadway, Market Street, all of these are getting affected. Okay, so all of these locations that we identified, we did see high flood depths during our modeling of design rainfall scenarios, but here, for the brevity of it, I just want to showcase an overlay of Harborside Drive because we see that repeatedly, even with the 3D model and the 2D map that we have. So whenever we produced a flood event or model flood event based on the different flood events that had occurred, historical flood events, as well as model design rainfall scenarios, we saw that this street always gets blocked. Okay, one of the primary utilities that we have for our digital twin is a prediction of what if scenarios. And to demonstrate this capability, we modeled design rainfall scenarios in the Galveston County using the IDF parameters that we have displayed over here. And we modeled it for 2-year, 10-year, 25, 50, and 100-year periods. We did a 24-hour simulation of the rainfall. Okay, and we see that we can get really highly localized view of the temporal flood depth and velocity. We'll come to that velocity later. For brevity, we are just demonstrating here the highly dense zone, so the northern part of Galveston. And here you can see whenever it gets to the 100-year period, the Harborside Drive near the port, the bottom right corner of its bayou, the Broadway Avenue, these get really quickly inundated. And then this is the maximum flood velocity that we can get. Now, for this is really useful probably for other cities with slope, but Galveston is a very relatively flat city. So if you see the legend over here, the velocity really does not hit a lot of critical levels. But you can notice that most of the high velocity water is near the main roads and where it's draining into the offsets bayou. Okay, so our digital twin also deliver critical insights of how infrastructure gets affected. It can be residential, it can be economic, it can be public utility, critical, non-critical infrastructure. Here, I'd like to highlight a few critical infrastructure facilities that experienced high flood levels. For example, if for school, the Uphill Elementary Magnet campus of Coastal Studies got affected most. For colleges, Texas A&M Galveston. For hospital, Galveston Island Community Service Center at Fort Flow. Then park, Moody Gardens Golf Course, neighborhood, historic downtown of Galveston, roads, Harborside Drive, and like I said, this keeps coming back into it. Okay, so let me present some quantified flood impacts here. We see that the percentage of buildings flooded ranges from about 67.78% to, which was in a 2-year flood event, to 79.5% in a 100-year event. Now, for buildings, it went from 0.5% to 6.2%. And 720 million square feet of area was totally flooded during a 100-year period. And here you can see for the different scenarios, how much total flooded buildings were there, and buildings that are flooded above 1 feet, maximum velocity there, and the road that was flooded above 1 feet increase as well. So we see that the buildings inundated by above 1 feet increased by 5.7% when we went from 2-year to 100-year flood, and road inundations increased by about 6.7%. And this was a complementary case study that we did alongside. So we analyzed how long the flood water remains after, say, a 6-hour storm. So the design storm was for 6 hours. We stimulated it for a total of 24 hours to see how long the recessing limb is, if the flood stays or recedes away. So we can see on the top over here, these are some of the most vulnerable neighborhoods. You can see there after a 6-hour storm, over 18 hours to 24 hours, even in 2-year rainfall, there is water remaining. And for an actual flood occurrence, this duration mapping would be very valuable so that we can direct our rescue efforts to these neighborhoods. Okay, last but not the least, we have the real-time flood forecasting, which is a critical component of our Galveston digital twin. And this would enable early warning systems to function more effectively, offer really timely efforts to emergency management teams. And here we have implemented it. We connected it with NextRad radar system in the Galveston and use that to give you real-time flood forecasting. Now, this does run into a bit of a latency issue based on where we run it, but when we can host it into high performance computing systems, we believe this can uh, get through that or remove that limitation. So this work had been published in CUS, which uh, for FlowsDT, Geospatial Digital Twin, and these are my co-authors here. This was funded by NSF NASIM Gulf Research Program, NIH, and CHI Educational Grant. You guys can look into it in the DOI given here if you're interested in it. And finally, I want to talk a little bit about the future directions of this. So our framework here is, we suppose it's not Galveston specific. It can serve as a transferable blueprint. So for coastal inline coupling, we can use this. We can integrate some storm surge models like Slosh. We can integrate that with FlowsDT using a storage tank on the coastal areas, same as we used outfalls at every grid point. We can connect that in and get results for compounded flooding. We can get building level risk classification, and I showed you some examples of that. For residential, commercial, and critical infrastructure, we can get effectiveness of structural interventions. That's a future study we are doing for low impact developments and pipe upsizing to mitigate the disaster. And IoT sensor integration, if we can make that kind of infrastructure, then we can have continuous real-time data. We can optimize our sensor density based on optimization algorithms. We can also do subgrid modeling for cities where we do not have as much sewer network data, detailed sewer network data. And we can also do NPS pollutant tracking, which would model non-point source pollutant transmission. And this is a next generation of our work that I'm interested in, the socio-technical geospatial digital twin. This framework sort of couples infrastructure physics, the artificial intelligence, and human behavior modeling through the three parts that you can see over here. So first, hybrid physics AI modeling, we can embed the shallow water equations that we saw in the governing equations before into neural network loss functions through the pins that we have, physics informed neural networks. And the subsurface flow, we can use graph neural networks. So we can get order of magnitude speed up here from our physics-based model that we had before. And secondly, we can use the multi-source data assimilation using ensemble Kalman filter. So when we have, say, IoT sensors, with weather data, satellite data, or even if we have soft kind of data like social media, news reports, or any kind of reporting app, we can use that, integrate it with the Kalman filter with different weightages, and improve our model continuously. And finally, we can have the human infrastructure interaction through agent-based modeling. So we can simulate, say, suppose evacuation traffic bottlenecks or economic stressors or business closures and capture a feedback loop, all of these. So a little bit of elaboration on the hybrid physics AI approach. So we can get the pins, get mass and momentum conservation equation and put it as hard constraints in the neural network loss functions. They can get the 2D surface flooding across different terrain models, and based on how the terrain slopes are, we can change the mesh sizes. For the graph neural networks, they can model the storm sewer system as a graph. We can have the junctions as the nodes or the conduits as the edges. They can learn the flow routing or surcharge, backwater dynamics. And these are just conceptual for now. And the coupling infrastructure, we get the rainfall input into the 2D surface spin model, the 1D sewer GNN model, coupled prediction, and get a real-time flood map. So our data sources would be physical sensors, remote sensing that we used one of them before, crowdsourced soft data that we can incorporate using the Kalman filter, infrastructure feeds from the pump station status, road closures, part grid state. And in the filter cycle, we can do forecasting, run all of the surrogate models going forward. We can observe the heterogeneous sensors, soft data that we have, analyze the Kalman grain, and update it based on that, the physical model that we have. And we can repeat this. So our main key challenge is having the confidence weight to be more focused towards concrete updates compared to the soft data, and how we can sort of balance that. For example, citizen report would be more spatially fuzzy. Picture or, sorry, not picture, a gauge report would be more accurate. Okay, so for the human infrastructure interaction, we have the residents, the drivers and commuters, how they can do route choices affected by the road flooding that we have. The business owners can figure out when to close based on how the floodwaters are approaching, and facility operators can use this to make decisions about the backup power, how they want to pump, if they want to open shelters, all of that. So from FlowsDT to socio-technical DT, we can see that our modeling was before physics-based PCSwim, so it took hours per run. Hybrid pin, GNN surrogates would be much lesser because they're surrogate models. They are not sequential. We can parallel process this. Data, we just use rain gauges. Rather, here we can use multiple of those using the filter. Human factors, we did not model it during the current study that we have. Here we can use agent-based modeling for the evacuation, traffic, or business closures. Assimilation, we can have manual input update. Here there is a continuous update, so it sort of goes into the digital twin environment field that we talked before about. And for scope, we had this in Galveston only. Here we would focus on Galveston as a coastal city and then Baton Rouge as an inland city. So it is a transferable blueprint to any city around the United States. And the output would be here flood depth and velocity maps. Here we can get flood maps, economic impact, service continuity metrics, and so on and so forth. So cyber infrastructure and iGuide, as where it can come in is we are going to use the supercomputer that we have over here with these facilities to train our deep learning surrogates model, run our ensemble forecasts, and we can use that for our city level of PIN and GNN training. And we can host this using the iGuide Geospatial Cyber Infrastructure for our workflows. We want to package this all as open source and reproducible so that most of the cities can adapt this framework using their data sets. And resilience dashboard so that we can have an interactive web-based tool for the emergency planners, managers. We can get real-time flood visualization, infrastructure impact forecasting, get predictions, and it can work without the local software that we needed. So scalability will depend on data requirements. So many places would have these high resolution elevation data, drainage system information, but if not, we talk about subgrid modeling, and then rainfall gauge data, topographic adaptations, as in the mesh cells needs to change based on what, if there is a steeper slope or not. We need a lot of stronger partnerships between research teams and city departments to get this into mainstream. And we can use iGuide as a platform that provides our cyber infrastructure and the compute resources and the collaborative environment that we can use to replicate FlowsDT to the other communities that we have. So before concluding, let me just briefly touch upon what the broader research community is pursuing on the digital twin space. We see that there is hybrid approaches combining data-driven speeds with physics-based accuracy in different other fields. Virtual and augmented reality, we see that interfaces for flood risk communication, multi-hazard, multi-domain digital replicas, web streaming of 4D visualizations to stakeholders, and then different social vulnerability metrics, environmental equity, justice metrics. We can incorporate all of that into digital twin analysis as well. Okay, so these are our key takeaways. FlowsDT can demonstrate that geospatial digital twins, if we have it with the 1D, 2D coupled hydrodynamic model, we can simulate urban flooding with really high spatial resolution, spatiotemporal resolution. And this advances urban digital twins to a level of detail 4. We can see that previous studies only have it over land. This integrates underground storm sewer networks, so significantly enhances the functional resolution that we have for flood analysis for digital twins. And we have the immersive 4D visualization, which sort of transforms the flood data from expert-only outputs to stakeholder accessible, more intuitive experiences. The architecture is more transferable to other communities and can be hosted in platforms like iGuide for various collaborative and reproducible research. And the socio-technical geospatial digital twin that we are pursuing now, it would integrate three different innovations: hybrid pins, so physics AI modeling for the speed of it, the multi-source data assimilation for accuracy, and then agent-based modeling so that we can have the human infrastructure coupling. So that's it from me. Thank you. I want to conclude the presentation, and I'm happy to take the questions.
All right. Thank you, Debayan. That was really comprehensive. I had not appreciated how extensive things were. We have a couple questions as people encourage you to ask them in the chat, but maybe I'd like to kick this off. I'm wondering if you could say anything about how you have coordinated or been in touch with or connected with any of emergency management planning and services within Galveston itself. I mean, you're using so much of their very localized data, and it's such a complicated city overall from a flooding history. How have you connected with them?
So there was a meeting with the city authorities there who work with the Texas Sea Grant, and we showed them how this model works. They are definitely interested in the hyperlocal flood forecasting that we have, because they can figure out where to send their emergency responders to. But we are still in talks with them because most of our work has used commercial softwares for
Mm-hmm.
now, and that's the talk at this position. But they are definitely interested in the results, and if we do have a surrogate model, they're more interested in that as well.
Okay. Yeah, that's important, trying to figure out how to best convey these important methods and results and to the on-the-ground stakeholders there. Um, uh, we have a question from Andy Anderson, who I can read it out loud for everyone here. Is groundwater absorption significant and taken into account somehow, in particular in sandy soil, as one would find in Galveston?
So
Yeah, there's a second comment here, but you could probably see that too.
yeah, so we didn't really take in antecedent soil moisture for now, because our flood modeling events were didn't like the flood events that we had modeled did not have an antecedent event that had happened, but we did take into consideration the land use land cover, how much infiltration is going in with that Horton infiltration method. But I believe if we need in the design rainfall scenarios, or if we want to model rainfall right after previous rainfall, then we can include antecedent soil moisture as well.
Okay. We have another question here in the chat from Sina. What is your platform currently based off of, and how do you visualize 3D models? He's wondering whether it's Esri. I think I did see that you were using
So
Esri for
we are
some of your viz. Yeah.
so we are using Storm City for our 3D visualization and 4D visualization, and that is based on a Canadian company called CHI, Computational Hydraulic Informatics, I believe. So that's what we use. We did try to convert this into Unreal Engine, and that has been useful so far. but it doesn't do real-time coupling with the PC Swim software. However, we can get the results and then project it into the Unreal Engine for making a visualization dashboard.
And is that part of what you anticipate to
Do
do
in
as
the
a next step?
Yes,
Okay,
because we want this whole stack to be in the open source, so we need to get into these softwares.
super. Okay, one of our audience has a hand raise. Sakawat Tanim, if you'd like to try unmuting your microphone and asking the question. And
Thank
Sina
you.
has a, yes,
Thank
I'm
you,
sorry.
Devan. Great presentation, much helpful for me. My question about we are also working on a similar kind of concept in South Carolina. And the main thing what we are suffering, I saw that you have data of utility, water line, etc. So getting those utility data was big challenge for us because for transportation data it is pretty open, but utility network is not that open. It's based on utility provider, and they sometimes when the capacity is low, they don't have the network built for them. So how did you handle that problem of utility data? And when you are talking about transferring to other community, which is a lower capacity community, which does not have that data, do you think that we need to make the data for themselves in that case?
We can make surrogate data for that. It does not exactly look like the sewer system network that we had for this purpose, because we had very extensive data, but we can look into subgrid modeling to replicate the behavior in case of smaller cities where we do not have exact information. But we have to look into different historical events first to make that grid. So we incorporate the hydrological parameters in the meshes that we talked about, and that sort of acts as a surrogate for the underground system. And it can be used as a stand-in before we have any storm sewer systems available.
Okay. Yeah, thank you, Devin.
Okay. Sina, your hand is raised.
Sure. Thank you, Dana. Thank you for great presentation and thank you for your answer. I really liked to hear that you are moving towards something that makes this reusable in future. One comment that I have is that look into an standard and an implementation called MUDDI, MUDDI. That is for underground, basically infrastructure that has been used in UK, has been used in New York actually as well, and it is for basically modeling the whole infrastructure that is underground. Because you probably know, like some places there are layers of these on top of each other, so they might have more complex connection system than a simple like a like it seems like a two-dimensional like a utility network. It might be very more complex, right? I'm not too sure how the data will be published. That is something that I'm hoping that cities like New York will be a role model for other cities so they will see the benefits. And especially your use case for the digital twin would be a perfect scenario and example for that.
Thank you. I'll look into this that you mentioned. Muddy, right? Yes.
Yes,
Thank you for that.
MUDDI.
I put the link to that in the chat here. Sina is a colleague of ours at iGuide. He's with the Open Geospatial Consortium, OGC, and of course would know a lot about the importance of how we can implement these standardized systems for models to expand their utility. Thank you for sharing that, Sina. Any other questions from the audience? If not, really appreciate everyone's attention and good questions. This recording will be processed, the file, and the recording will be up on our VCO webpage, usually within just a few days. We're excited. Debayan's going to be one of our leaders at our summer school this year. It's taking place in July in Illinois, so we'll have a group of participants working on some of the his models there. And we've got lots of other VCOs coming up on a weekly basis, so do check out that webpage for registrations for these. And Anand, any final comments from you?
No, thank you. I guess, Debayan, thank you. Yeah, and as Diana said, we have more VCOs coming up. Also, the forum and HDR conference. We have position papers as well as posters and papers that are due, I guess, tomorrow. So
Tomorrow.
yeah, so it is a short notice, but yeah, things have been going out in our social media as well as other channels. So hopefully you have been aware of it. If not, I guess check out on our website as well.
Yes, I will put the link to our VCOs here in the chat and also our call for participation for these forums. We'll have posters, workshops, position papers, and other short papers. And most of these just require a very simple little abstract to get started. So something that shouldn't be any problem in putting together in a short call. I'm going to quickly put this forum link here in the chat space. So. Okay, thanks very much, everyone.